All right, hello everyone. Today in this video, we're going to discuss about a very important feature of studying physics, and that is how you represent mathematical correlations. Of course, if I put it that way, it might seem very abstract. However, expressing mathematical correlations are extremely important in physics because you might have heard that when you are doing experiments, you have two quantities between which you seek to find a functional relationship. You have an independent variable which you vary on your own, and you have a dependent variable which varies along with the change in the independent variable. So the entire experiment is aimed towards finding a relationship between the two of them. So that is what I meant when I said establishing mathematical correlations or establishing functional relationships between physical quantities. And that's what physics does. So today we are going to do a very simple exercise. Again, I'm using the Vet Colorado website where you have curve fitting simulations. Now, as we start, what I'll first do, as you can see, there's a grid over here, a graphical plot, the y-axis, the x-axis, and there are data points over here in this bucket, though I don't know why they have put it over there. It's kind of encroaching upon the graphical space, but nonetheless, let's just keep it as no fit. Now let me put a point over here, another point over there, another over here. All right, as you can see, let's try for a best fit, right? Now you see there are numerous choices as to how you can choose a best fit. I chose no fit, that's why there is nothing on the graph. I choose linear, that's what you see. A straight line through all the points and passing through the origin. Well, actually not the origin, because there is an intercept over here, and the equation is of the form a plus bx. Maybe if I move it around a little bit. So you see the a part, the a coefficient over here is 0.03, which is very close to 0. So for all practical purposes, I can consider this equation to be a straight line passing through the origin. Okay, so when the intercept is very, very small and it's very close to 0, then we can, for all practical purposes, consider this line of best fit to be a straight line passing through the origin. And what does that mean? If the line of best fit between y and x is a straight line passing through the origin, then that means y is directly proportional to x. So please remember always, whenever you have two quantities that are directly proportional to each other, it means they're represented by a straight line passing through the origin, right? Okay, let's clear it again. All right, so again we have a straight line, no doubt, a straight line, but it doesn't pass through the origin. There is an intercept. So the equation is of the form y equals to mx plus c, or y equals to a plus bx, as they have mentioned over here, a being the intercept, the y-intercept in this case, and b is the gradient. So for a straight line, of course, we know that the gradient is constant everywhere, no matter any two pair of points that you take from the straight line. If you calculate the gradient, you would get a constant gradient. Now, in this example and the previous one that I showed, the gradient is positive, right? As you saw, it was positive, 0.778. The previous one was probably 1.234. So they were both positive, right? So a positive change, which means As y increases, x increases too, and they both increase in the positive half or positive quarter of the quadrant, right? Where y and x are both positive. Now, if I look at something like this, all right, what changes do you see? Now the intercept is no longer, intercept is along the y-axis, right? It's still there, but there's an x-intercept also. However, that is not of much importance to us because we are only focused on the y-intercept, the point from where the graphical representation starts, because that's the initial value. That is the initial value of the functional correlation that we consider. And that more often than not has some physical significance. Now, the other thing, the gradient, look at the gradient, it's negative, right? So a negative gradient represents a negative correlation, if I may say so, which means that as x increases, y in fact decreases. Now this can be kind of related to a unit, say for instance electricity. A non-ideal cell, a non-ideal battery which has internal resistance, if you draw more current from it, then the voltage in the external circuit that decreases. So if you plot a graph of voltage versus current for a non-ideal cell, the graph would actually look like this. And this intercept would represent the EMF, the maximum voltage that the battery can supply when it's not connected to any external circuit. So as it's connected to an external circuit and the current drawn from the battery increases, the lost volts increase and the voltage delivered to the output circuit, that also goes down. So a negative gradient represents this sort of a negative correlation. All right. Now we turn our attention to this quantity, which is r square. R square is 0.99. Now, as you can all see, the points that I chose, they are roughly lying on the line itself, right? What happens if I move these points a bit away from the line? What's happening? The r square value, in fact, decreases. The r square denotes the strength of the correlation that you chose, right? Now, what do I mean by strength of the correlation? As you see this black line, this signifies the deviation, standard deviation of the value from the mean values that are used to draw this line. Now, as the deviations increase, you see the red bar over here, the correlation has actually lost its strength, its reliability. It's not reliable anymore. So maybe a better fit would be given by this. Perfect. A quadratic fit is now what is more appropriate for these set of points. So this exercise was actually aimed at making you realize two things. One, how to decode a graph by looking at its gradient and intercept, and to make you realize that the line of best fit is not always a straight line. And what is the difference between a straight line passing through the origin and a straight line that does not? So that's all for today. See you later.